spectroscopy. In short, we can seeing the unseeable. What I mean, in this particular technique, we use electromagnetic radiation as a probe to obtain information about atoms and molecules that are too small to see. When we have very tiny atoms or molecules, we need to understand their structure, and that can be done with the help of electromagnetic radiation as a tool. That is called as spectroscopy, seeing the unseeable. What happened? The electromagnetic radiation, which are having speed of light in vacuum. Okay? And here we treat this electromagnetic radiation as a wave, or consider as a wave nature of this electromagnetic radiation. When we talk about few important relationship of a wave and its few terms, then we all know that lambda represents the wavelength, mu represents frequency, c is the speed of light, e is kinetic energy, and h is the Planck's constant. So we have universal equation E is equal to h mu, and then we have these different relationships. So here one can understand the wavelength is inversely proportional to frequency, energy is directly proportional to frequency, and energy is inversely proportional to the wavelength of that electromagnetic radiation. So these few formulas are important when we discuss spectroscopy and particularly use of electromagnetic radiations. Now there are different regions of electromagnetic radiation, and to mention a few, okay, here we can have radio waves, okay, then we have infrared radiations, we have visible light, ultraviolet light, X-rays, gamma rays. In today's discussion, we will be focusing on these infrared radiations, which are having the frequency range from 10 raised to 11 to 3.8 into 10 raised to 14 meters. Whereas when we talk about the wavelengths in hertz or in the frequency, which is 3 into 10 raised to minus 3 to 8 into 10 raised to minus 7. So what is IR spectroscopy and what are molecular vibrations? That we need to understand. In today's discussion, we'll be focusing on introduction, principle of IR spectroscopy, theory of the molecular vibrations, what are molecular vibration and how they can be observed, different vibrational frequencies, and number of fundamental vibrations. So moving towards next. Now first we need to understand what is vibration in a molecule. It can be defined as any change in shape of the molecule. That change can be because of stretching of bond, bending of bonds, or internal rotation around single bonds. Now, when we talk about the vibrations, which are those wavelengths responsible for causing the changes in these vibrations? The answer is simple. Infrared radiations, which causes vibration in the molecule. These infrared radiations are having wavelength from 0.8 micron to 200 micron. This is the region of electromagnetic radiation, which is referred as infrared region. Now talking about IR radiations, we said the infrared radiation causes vibration in a molecule. What are IR radiation? These absorption of higher radiation are quantized, okay? And they causes various bands in the molecules because of the stretching and bending with respect to one and another. The higher region is divided into three parts, and these three parts are according to the position of this higher region with respect to the visible region of electromagnetic radiation. 0.8 micron to 2.5 micron is termed as near IR region, which is obviously we can say near to the visible region. The mid IR region, 2.5 micron to 15 micron, is very important. Okay. For organic chemists, most of the functional group will get absorbed in this region, and therefore we'll be focusing our study between this 2.5 micron to 15 micron. It is termed as mid IR region. And the third is 15 micron to 200 micron, also termed as far IR region. So, which is the farthest from the visible region. These frequencies of higher radiations are conveniently expressed in wave numbers. Usually, we express frequencies using hertz, but for IR spectroscopy, it is conveniently expressed as wave number. So, how to convert the frequency into wave number? So, here one can understand 1 micron is equal to 10 raised to minus 4 centimeter. So, if I want to convert it into wave number, okay, the unit of wave number is per centimeter, then it will be equal to 10,000 divided by wavelength in micron. So here you can easily calculate the wave number if the wavelength is given. What we observe, as the wave number increases, wavelength decreases. So here we can say wave number is inversely proportional to wavelength. Talking about vibrational frequencies, when we say the molecules vibrate, we need to understand that the bonds in a molecule are not rigid, okay? And they behave like spring with mass attached at the either end, and they obey Hooke's law. What is Hooke's law? Force is equal to minus kx. Okay? And if I want to calculate the frequency of vibration, then the value can be substituted, and it is nu equal to 1 by 2 pi under root k divided by reduced mass. And reduced mass for a diatomic molecule can be calculated in the formula m1 m2 divided by m1 plus m2. Infrared radiations are having thermal energy. Okay? And what they induce? They induce the molecular vibration in covalent bond. We say that when the molecules are considered as a spring, or these covalent bonds are considered as a spring attached with two masses or two atoms. So this can be depicted in this picture here. These covalent bonds are like the springs, whereas the atoms are the two masses attached to that spring. And when we have the vibrations, okay, then we can say we can stretch that string, we can stretch that bond, we can compress that bond. Okay? So these types of vibrations can be observed. It is important to note that specific bonds absorb at specific frequencies. This is the important point to study the spectroscopy or IR spectroscopy in organic chemistry. So specific bond or specific functional group absorb at specific frequencies. Now let's see factors affecting these vibrational frequencies. There are two important factors which causes change in the vibrational frequency. First of that is the masses of the atoms attached to the particular bond. And it has been found that the lower the mass, higher is the vibrational frequency. If we compare the vibrational frequency between CH, CC, Cn and CO, as it is stated that the stretching frequency will go on increasing. Okay, so mass will be the lower and the frequency will be higher. The second factor which affects the vibrational frequency is strength of a bond. So here you commonly observe examples which are written, and it has been found that as the bond strength increases, the vibrational frequency increases. Okay? So this is how we can compare. Next and very important point is vibrational modes in a molecule. For every molecule having n atoms, the positions of all n nuclei depends on total of 3n coordinates. That is, a molecule has 3n degree of freedom, including translational, rotational, and vibrational. A non-linear molecule can rotate about any three mutually perpendicular axes, and it has 3 rotational degree of freedom. Whereas for a linear molecule, the rotation is only possible for 2 degrees. So that is called as 2 rotational degrees of freedom. Because above the molecular axis, the movement of atomic nucleus are not possible. And when we talk about the fundamental modes of vibration in a linear molecule, it can be calculated by using formula 3n minus 5. So for a linear molecule like carbon dioxide, n is the number of nuclei or number of atoms. So carbon dioxide having 3 atoms, 1 carbon, 2 oxygen. So if I substitute the value n equal to 3, then the number of modes of vibration in a carbon dioxide will be 3 into 3, 9 minus 5 will be equal to 4. And that for the non-linear molecule can be calculated using 3n minus 6. So for a molecule like water, which is also having 3 nuclei or 3 atoms, 2 hydrogen and 1 oxygen, then n is equal to 3. So 3 into 3, 9 minus 6 will be having 3 fundamental modes of vibration. The different modes of vibrations which are important for organic chemists are here in this picture. You can see we have symmetrical stretching, we have asymmetrical stretching, then we have bending vibrations like rocking, wagging, twisting, and scissoring. So these are the 6 important modes of vibration in a molecule that we will be studying when we discuss IR spectroscopy.